In this video, we're going to cover galvanic cells, or also known as voltaic cells. Take a look at this image on the left over here. You can see that there is zinc solid, and inside the zinc or outside of the zinc solid is copper sulfate solution. The copper sulfate solution over time will change into something that looks like this. Well, what's happening? The copper is no longer in solution, but it is becoming solid. Whereas the zinc that was a solid before now comes out into the solution, forming into zinc sulfate solution. In other words, if I were to zoom this in, magnify this in a considerable amount, then we can see this zinc forming into a zinc solution, meaning it's coming out from the solid state to aqueous state. Whereas a copper 2 plus, where it was in aqueous state, now forms into copper solid. I can put this in a process in which we have the left and right side of the equation, this particular reaction here. We have a zinc solid, that's this form, forming into zinc aqueous with the +2 charge, meaning that it's going in the solution. Whereas a copper 2 plus, that was the solution, now forms into copper solid in this formation. This process is considered to be thermodynamically favorable, meaning it happens spontaneously. Let's divide this into two half reactions. We have oxidation on the left-hand side, and we're going to put the reduction on the right-hand side. So here's my oxidation reaction and my reduction. Oxidation, we have zinc solid forming into zinc 2 plus. Well, how many electrons has it lost? Well, zinc right here, oxidation number is 0, whereas zinc on the right-hand side, the oxidation is +2. So that means there was 2 electrons that was lost from this oxidation reaction. Now, for the reduction process, we have copper aqueous, and that's +2 charge, and it gained 2 electrons in order to form a copper solid. How did I know? Well, the oxidation reaction or oxidation number for copper 2 plus is +2, and for copper solid is 0. So therefore, you need 2 electrons to gain in order to go from +2 to 0. Through this oxidation number, we know how much electron is being transferred. In fact, the electrons transfer from the zinc right here that it has lost. Well, the copper gained those 2 electrons. So we can say that this is, the equation above is by moles, and by charge it is balanced. Now, why is this important? How does this relate to the galvanic or the voltaic cells? Well, let me show you an image of a voltaic cell, and it looks like this. A galvanic voltaic cell, the zinc and the copper are in a separate component. It's in the separate cell. Over here, the image shows that it's in the same cell. But if you were to take the zinc on one side and copper on the other side, and even the solution, we have zinc sulfate on one side and copper sulfate on the other side, and we connect it through a wire and what's also called a salt bridge. We'll talk about all the details in a moment. This entirety is called the voltaic cell. And now, why is this important? Well, this is important because we can this reaction is thermodynamically favorable, because it means that zinc wants to lose the 2 electron and copper wants to gain 2 electron. It's thermodynamically favorable. Well, as that favorability happens, the electrons will travel from the zinc side to the copper side. And copper side will accept those electrons because they want to gain the 2 electrons. Having this thermodynamically favorable reaction can generate what is called the electric current. An electric current is just the flow of electrons. It's a movement of electrons. Having this movement of electrons can actually get you the light bulb, right? Or it could turn on a particular device. So having this, again, thermodynamically favorable reaction will generate an electric current or electron flow, for this particular case, from going from the zinc to copper. Let's dive in a little deeper and in more details in the next slide. So in this slide, it shows more of a zoomed in version of that Voltaic cell. And you can see all the little components, and I'm going to address all the components in a moment. So this device right here, also known as the voltmeter, the electron flow is going through there, and it's going to measure the electron flow. Okay, it's going to be measuring electron flow through there. On the left-hand side, or this entire cell, this is where the oxidation takes place. This is where the zinc forms into zinc 2+. So let's write that. Zinc solid is forming into zinc +2, and it's losing 2 electrons. So this portion over here, here's my zinc solid, and it's forming into zinc 2+, as you can see, from going from here to it's going in this direction, and this is where oxidation is taking place. They're also known as the anode. On the cathode side, or the positive towards positive side, this is where cell reduction takes place, where the copper 2+ forms into copper solid. So we have where copper 2+ aqueous accepts that 2 electron from the zinc and then forming into copper solid. So here's my going into anode. It lost 2 electrons, so zinc became zinc 2+, and that electron is going to flow in this direction, passing through that voltmeter, and the voltmeter will measure, how's the electron flow? Is it moving? Are a lot of electrons moving? Are they not too much? Okay. And the electron is coming here. As the electron is coming here, it's going to give the electron to the copper 2+, and the copper 2+ will become copper solid. Now, there's also this component known as the salt bridge. Not as important. It's not going to be tested, but I do want to mention it real quick. The salt bridge helps with, there's going to be a charge built up here. And because there's a particular charge built up, the salt bridge, all it does is make sure that there's no, it's to make sure that electron flows in this direction, okay? It's just to help with the flow of the electron, and it doesn't stop. So let's do a learning check. Here you see another galvanic cell is fabricated by connecting 2 half cells with a salt bridge. One in which a copper solid is emerged right here in the anode, and then you see a copper nitrate solution. And the other one, you see a silver solid emerged in 1 molarity of silver nitrate. Write equation for the anode half reaction and the cathode half reaction and the overall cell reaction. So it's wanting to know what's going on in the anode, what's going on in the cathode, write the half reaction. So let's go with the anode first. So anode. In the anode, we have the copper, okay? And then we can see that the copper is forming into copper 2+. We have copper solid, and that's going into copper +2. And this is an oxidation. Remember, anode is where oxidation reaction is occurring and the electron is pumping out, and so +2 electrons. Then we have our cathode. Let me write this oxidation process, okay? These are together. And then we have our cathode and that's where reduction is happening. And we have our silver plus, okay, silver aqueous 2 plus, plus 1, forming into silver solid. And we have 1 electron that's going to be added. I rewrite this, it's all messy. Now, how did I know it's 1 electron? If you kind of think about the oxidation numbers, you can tell how many electrons are being pulled out and how many electrons are being pulled in. So oxidation number for copper is 0 and copper 2 plus is +2. So you must take out 2 electrons to become +2. For silver, in order to go from silver plus to silver solid, it has an oxidation number of +1. This one has an oxidation of 0. Therefore, you only need 1 electron in order to neutralize that +1 to 0. Now, this is what's happening. However, you'll notice that the electron number is different. We need to have it so that the electron number of the anode and the cathode are the same. And this is deprived of 1 more electron. We're going to go ahead and multiply all of this thing by 2. So you have 2 silver plus 2 electrons forming into 2 silver, like this. Now I have the anode and cathode balanced out. Now we can go ahead and take the overall reaction of this. If you look at the top one and then you look at the bottom one, we could cross cancel out the 2 electrons like this. And go ahead and rewrite the overall reaction, okay, below. And the overall reaction is that copper is on the left side, so is silver, Ag, Aq. And then we have the copper 2 plus on the right side, 2 silver solid. Okay, so we have this whole process where you have copper 2 plus, 2 silver, and 2 silver solid. All right, so that's the overall cell reaction. So what's the answer if you want to know? The equation for the anode half reaction is written here. Let me get this highlighter. So anode half reaction is right here. The cathode half reaction is this one right here. And then the overall cell reaction is all this on the bottom. There is a particular notation that we can utilize this cell, meaning that we can't always be drawing this image to show what's going on, but there is a particular notation, also known as a cell notation, that allows us to see what's going on in the cell without drawing this picture or having that picture all the time. The cell notation looks something like this. There's a bar and 2 bars and another single bar over here. Well, what this is showing is there's a zinc on the left, okay? This is the zinc solid that forms into zinc 2 plus with the aqueous. So what is it oxidizing to? Then on the other side, you have the copper 2 plus. That's the one that is going to be about to be reduced to copper solid. And you notice that there is a line in between to show that where it's going from one state to the next. And this one is going from one state to the next. Then there's this double bar over here. So on the left-hand side, again, it's the anode or oxidation reaction. On the right side, we write the cathode reaction or the reduction reaction. That double bar in the middle, that's the salt bridge. Okay, it's showing, it's an image of the salt bridge. Please take into consideration that solid on the left and the right, it always starts with the solid and ends with the solid. So we don't write zinc aqueous and then, solid aqueous and then solid aqueous. It needs to start with the solid and ends with the solid to show the entire cell notation. So we can go ahead and try writing the cell notation based on the following reaction. We'll try it for this one, and then you try this one and check the key. Let's write a cell notation based on the following reaction, and this shows that aluminum plus copper forming into aluminum 3 plus and then copper solid. So pretty easy here. We have aluminum solid forming into aluminum 3 plus aqueous. Then we got double bar showing the salt bridge. And then we have the copper 2 plus. And that's going into copper solid. So everything here is what's happening in the anode. And this right here is whatever is happening in the cathode. So go ahead and try the cell notation for the next one and come back and check. And here is the key.